Okay, for people who are following along at home, can you please raise your hands if you can see my screen and hear me? Okay, perfect. Okay, great. You can take your hands down. I appreciate it. Okay, so let's get started. And I kind of want to give you an overview of where we've been and where we're going because we're at a transition today. We have been talking about how, if you are already given a database, how you can query that database in order to perform what we call CRUD operations: create, read, update, and delete. So manipulation of the data. And then we've talked about, if you have a design in hand, how can you create the database using the data definition language. Today, we are going to finish up with data definition language by talking about views. And then we're going to talk about the theoretical foundation for SQL, specifically the data manipulation portion of SQL, which is the relational algebra and calculus. After today, we move to a new segment of the course where we'll be talking about design. So first entity relationship modeling, then normalization, and then physical design. So for the next 3 weeks, we'll be talking about how you design the database, both at a logical level, which is the entity relationship modeling and normalization, and then at the physical level through physical design. Okay, and I had a good question before class, which is on some of these complicated queries, it can be difficult to figure out how to get started with them. So on homework 2, I intentionally gave you some more difficult queries. The very first one, where you're printing out details for all rooms, even unoccupied ones. And it can be difficult if you start and say, okay, I have to figure out what are the database operations to do it. My recommendation is, if you're struggling, first figure out how you would do it by hand. That is, if there was no computer, and I simply gave you these tables of data and said, compile a report for me that, in this case, gives me the details for all rooms, even unoccupied ones. And if it's occupied, give me the name of the person in that room. We'll figure out how you would do it by hand. If there was no computer, if this was the 1700s, and I kept some of this data in different ledgers. And now I come to you and I give you several books with this information, and I say, okay, I need this report. How would you do it by hand? And once you figure out how you do it by hand, well, actually, you should be able, the way you do it by hand, there should be analogous database operations that will allow you to do it in the database. Okay, so that's my hint on how, if you're struggling, how you might get yourself out of that struggle. Okay, so we do have a lot to cover today. As I said, we're going to first finish up with data definition language, talking about views. And then we will jump to the relational algebra and calculus. So you've already seen views when we talked about the relational model back, I think it was the second lecture. So it's a virtual relation that can be produced upon request. And sometimes it's cached, sometimes it's produced on demand. We'll talk about the pros and cons of each way of doing it. So here we have an example where we have a view with the number of properties managed by each staff person. This, you can tell immediately it's a view because you'd be unlikely to keep an aggregated column, which is count, in an actual database. So this is certainly a view. And as I just said, there's actually two ways that SQL or any other database system will support views. They can either immediately figure out how to generate that view by translating it into operations on the underlying what we call base relations, which are base relations are physically stored in a file somewhere, or we can do what's called view materialization, where we cache it as a temporary table. And then as the underlying base relations change, we actually update this cache table. Okay, before we get to how we implement views, we'll do that a little later. Talk about a couple of common types of views. So one is called a horizontal view, and it essentially selects a subset of rows from a table. So in that way, you restrict a user's access to only a portion of a relation, in this case, a horizontal slice of the relation. So here we are allowing a manager to view all of the details of his or her employees at branch B3, but not at the other branches. So the syntax is, instead of create table, create view, then you give the name of the view, then the keyword as, and then this is called the defining query. So that specifies the operations on the base tables that will be used to create the view. And thereafter, once we've named it, we could actually perform queries on this view. So for example, we could say select star from manager 3 staff. So once the view is created, we're allowed to write queries on that view just as if it's another table in the database. Now there's some restrictions on that, and we'll get to them, but you're able to write some queries on that view. So a second type of view is a vertical view, and it means that you can see the entire, all rows in the relation, but only certain columns. So it's a vertical slice. So in this case, we might want to create a directory of the staff at branch B3, but we want to exclude the salaries. So in this case, we specifically create a view and select the columns that will be in the directory. And in this case, it's also creating a horizontal view because we're restricting the branch to B3. If we got rid of the where statement, it would be a true vertical only view because we'd see the entire, all rows in the relation just with some of the columns removed. And then the third big use of views is to create a view that has one or more aggregated columns. So we started this by showing you a view that contained the number of properties managed by each staff member. And here's how we could create that view. First of all, you see I've added a comma-separated list of column names, and it is just like in a normal select statement. You can say something like s.branch number as or count star as. So these in effect become the aliases for the columns in the select statement. So in the view, count star will actually be named CNT. And the rest of this is just like you've seen before. So we're grouping on the branch number and the staff number in order to get the count. And then we are doing a join on the staff number and the, well, on the staff number. So if we just did the group by on the property for rent relation, we could get the staff, but we would not know what branch they belong to. By grouping by the branch number, that gets branch number into the group by clause so that we can also have it up here. Okay, otherwise, if it's not in the group by clause or an aggregated column, it's not allowed to be up here. So this is a bit of a hack because technically speaking, we should only have to group by staff number in order to get, presumably, well, not presumably, we only allow staff to be at one branch. So there's no risk that you could have the same staff member at two different branches. So this is really kind of a bit of a hack, but it shows you what you have to do if you want to get additional information into the view. Now, MySQL actually would probably support this query even if I didn't group by the branch number. And I showed you, I think last week, how MySQL could rearrange the query in order to not violate any of the restrictions on grouping. Basically, it could create a subquery where it would first do the grouping on property for rent, and then once it had that sub-result, it would join with staff. Okay, so this is the third common use of views. So horizontal views, vertical views, and views that use aggregate operations are the three most common types of views. And then the fourth one, and what I suggest you perhaps consider doing in the homework assignment, is creating a view simply as an intermediate result to break a complicated query into a series of simpler queries. Okay, so the view creation syntax, you've pretty much seen everything. The only thing you haven't seen is this with check option. And the with check option comes into play when you are going to try to update the view itself. So you can always update the base relations, and the updates to the base relations should be reflected in the view. But if you change the view, if you add a row or delete a row from a view or update some column in a view, you might want that information propagated back to the base relations. What the with check option says is we cannot add, delete, or modify a row in a view if it would violate the defining query. So for example, if we have a view that lists all properties that rent for more than $400, and we try to insert into that view a property that's only $300, if we do not have the with check option, it will be actually permitted. But if you say with check option, it would be rejected because it violates the defining query for the view. In fact, you should always use the with check option because it makes no sense to update a view in a way that violates the defining query. Okay, so that's what I just said. Okay, so as I said, you're allowed to, once you have the view, you can do queries on the view, which is helpful. Remember I said sometimes you want to create a query as an intermediate result. Well, if you couldn't use that intermediate result in another query, it would make no sense to create the view as an intermediate result. So it certainly helps if you can use a view in another query. So there are some restrictions on what you can and cannot do. So if a column in a view is based on an aggregate function, this is where you run into the most problems. it can only appear in a select and order by clause. It's not allowed to appear in a where clause. So for example, back here, I created this count column. You can't then say select count of count, because count is already an aggregated column. Okay, nor can you say select star from staff property count where count is greater than 2. And if you think about it, the reason you can't do that is because it would be illegal to do this in a regular query. You can't use aggregated operations in a where clause. You can only use them in a having clause. So I actually, because of time restrictions, got rid of how you do view resolution when you write a query on a view. But basically what you're doing is you expand the view into operations on the underlying base relation. So this count would be replaced with a count star, and you can't have an aggregated operation in a where clause. Now, I would be interested, I didn't look this up beforehand, it just occurred to me that if I change this where to a having, whoops, it might work. In fact, I think it would work. So I think if I instead said select star from staff property count having count greater than 2, it would work, because having is allowed to be used with aggregated operations. So MySQL takes a more relaxed view sometimes toward this. So these might work in MySQL, but in the SQL standard, it's pretty strict that aggregated columns can only appear in select and order by clauses if they're part of a view. But like I said, I would be very interested to see whether having might work here. Okay, so we're not going to discuss the updatability of views, and that's because we discussed them the first week of the course when we talked about the relational model. If you go back to the notes for the second lecture, so if you go back, I'll show you where. If you go back to lecture 126 on the relational model, you go to the slides, and toward the end of the slides, we talked about updating views. So I don't want to repeat what I already said, especially because I'm kind of time limited today, but you can see what are the restrictions on updating views. Okay, we also discussed already the advantages and disadvantages of views. Same set of slides. Go back, have a look-see at what the advantages and disadvantages are. So the last thing we want to talk about is how views get implemented. One way is on demand, and that's called view resolution. In that case, what happens is we translate the query on a view into the underlying a query on the underlying base relations and execute that. But if the view is frequently used, then that could put a lot of strain on the database's resources, because every time we want to view or look at the content, the output of that view, the query is reperformed. So the other way we might do it is to cache the table and store it physically on the database. The interesting thing then is how we keep that cache up to date, that cache version. So if there's updates to the underlying view, then we have to figure out what to do. So here you see this defining query. We are printing out all staff members that belong to branch 3 and manage a property whose rent is greater than $400. Okay, so here's some possible scenarios. We insert a row into property for rent, and the rent is less than or equal to 400. That's not going to have any effect on this relation because we only care about rents greater than 400. So that's an easy case. Okay, we insert a row for a new property with staff SG19 and the rent is 550. Okay, if you go back here, okay, the staff member is SG19. There is no staff member SG19 in this relation, but they now manage a property whose rent is greater than 400. So in this case, we would need to add that staff number to the cash relation. Okay, that's fairly simple. Okay, we insert a row for property PG54 at branch B3 with staff SG37 and rent 450. Well, the rent is greater than 400, but that staff member SG37 is already in the relation, so we do nothing. Deletions are the tough one. Okay, inserts are fairly easy because we can check and it's either something has to be added or it's already there and we don't do anything. Deletes are a little tougher. So let's say we delete property PG24. Well, we go back, I think, actually, you'd have to look at the relations, but second. So PG24, let's go and look at PG24. And I'm going to have to go to the handout for that. Okay, so let's take a look at PG24. Unfortunately, it's kind of small. So looking at, okay, here is PG. No, we don't even have PG24. Well, just a moment. So I'm going to make some assumptions since I don't have it. So let's say PG24 is deleted. Let's say its rent is 500 and, that's why we inserted it back here. So we inserted it, its rent was 550. When we did that, SG19 got added to the table. So if later we delete property PG24, then as long as we have not added another property for SG19 whose rent is greater than 400, then we would need to delete SG19 from the cached view. Okay, and finally, let's say that we delete property PG54. Well, up here we inserted it, and we know that there was already a pre-existing property for SG37 because SG37 was already in the view. So basically, if we delete a property that satisfies the condition that the rent is greater than 400, but that particular staff member manages another property whose rent is greater than 400, then the row should not be deleted. So we're not going to go into how the query optimizer makes these decisions, but this gives you a feel for what the query optimizer needs to deal with. There's, in this case, 5 different cases that would have to be dealt with. Okay, and then I didn't even deal with the case where there's an update to the rent. So another situation would be, let's say I increase the rent on a property, so it goes from $390 to $405. Then all of a sudden it would satisfy this condition, so we'd need to consider whether the staff member managing that property should be added to the table. So just trying to give you a feel for the difficulties and complexities associated with view materialization. It's a big advantage in terms of having the relation physically stored, so you don't have to rerun the query every time. But if you're updating it constantly, then that's no good either. So there's a trade-off. And you as a database designer actually have the choice of telling the query optimizer whether you want it cached or resolved on demand. And sometimes you don't know until it's in production whether it's right or wrong. You just have to guess. Sometimes you have a pretty good idea. Okay, so that's it for views. In this course, if we had more time, we would discuss transactions, which are a set of queries, and you want them either all performed or none of them performed. So if the database crashes in the middle, or if one of the queries crashes in the middle, like you have a script and you have a syntax error or something, and the third of the 5th queries crashes, then you would like it to roll back to the pre-existing state. Very complicated to do, involves locking and other things. We could spend a couple weeks talking about transaction management, but we don't have time. And then access privileges. So it's possible on a per relation basis to grant read, write privileges to users. So in addition to creating horizontal and vertical views, there's also other ways to control access to the information in a database. Okay, so any questions about views? Not sure if I had my speaker on, so maybe someone tried to ask me a question earlier and I didn't hear them. No questions? Okay. In that case, I'm going to move on to relational calculus and relational algebra. Okay, so we've already talked about a formal basis for the structure of relational database. That was when we talked about the relational model on the 2nd class period. Today, when we talk about the relational algebra and calculus, we are talking about a formal basis for the query language, for the data manipulation language. And specifically, what we're going to find is that it is the relational calculus which forms the formal basis for the query language. The relational algebra turns out to be a more procedural language that can be used by the query optimizer. So we'll talk about relational completeness, how you form queries in the relational algebra, how you form queries in the tuple relational calculus. So this is the second day where having 311 is kind of necessary for understanding what's going on. So that's why 311 is a prerequisite for this course. So As I said, informally, the relational algebra is a high-level procedural language, whereas the relational calculus is a declarative non-procedural language. And in fact, SQL is based on the relational calculus. Even though you will see very strong similarities between SQL and the relational algebra. The relational algebra is more or less a assembly language that can be used by the query optimizer to create a schedule of operations to perform a query. Okay. So basically, you can think of the relational calculus as the way in which we express a query. Okay, that's SQL. And then the query optimizer translates that query into a schedule or list of operations that are expressed in the relational algebra. So actually probably worth even putting down so that. So it's kind of the idea is that you have a query and it's expressed in SQL, but SQL is based on the relational calculus. And then that query is translated into a set or a schedule or list. Actually, I'll say a list of high-level DB operations. And that is the relational algebra. Okay, so this is a procedural list. So, as I said, it will look very much like SQL has a strong relationship with the relational algebra, and it does, but it is the relational calculus that is actually forming the theoretical or formal foundation for SQL, and in fact for the data manipulation languages in the relational model. So we say that any language that produces a relation that can be derived using the relational calculus is relationally complete. SQL is relationally complete. Any query that can be performed in the relational calculus can also be performed in SQL. The relational algebra is relationally complete. Any query that can be expressed using the relational calculus can be translated into a relational algebra query. Okay, so with the relational algebra, it satisfies some nice mathematical restrictions, namely that the output of a relational algebra operation will itself be a legitimate relation. So the output from one relational algebra operation can become the input to another one, which is critical since, remember, it was devised so that you could create a list of relational algebra operations to satisfy a query. Okay, so this property is called closure, meaning that any operation that any of the relational algebra operations that you perform will themselves produce a valid relation. And there are 5 basic operations and then 3 so-called convenience operations that are derivable from the 5 basic ones. So the 5 basic ones are select, project, Cartesian product, union, and set difference. The convenience ones are join, intersection, and set division. And I'll show you how join, intersect, and division can be derived from the other 5. Okay, so we have gone over, you should, selection and projection, we've done union, set difference, intersection, and join, we've all done. Cartesian product and division are the only two that I'm going to spend a little time talking about here. So Cartesian product is right here. It's just the combination of every possible pair of tuples you can get by, in effect, crossing P and Q. So A1, A2, A3. So you basically take any tuple in Q and append it to A, then you go to the next row in P, and again, append all possible rows of Q. Set division is the one that took me the longest time to get my head around. So I'll start by giving you some examples with set division, and then we can talk about the more formal basis. So let's say that I want to find, I'm the Tennessee Tourism Commissioner, and I want to get a list of all people who have visited all the parks in Tennessee. I want to celebrate them. I want to invite them to a ceremony. They are the ones who have completed a visit to every park in Tennessee. So I want to ask a query that essentially says, give me the names of all individuals who have visited every park in Tennessee. That is set division. Okay, another example. I am a hotel chain, and I wish to reward the guests that have visited every hotel in the chain. So I want to get a list of all guests who have visited every hotel in our chain. That's set division. Okay. So here's a more formal definition of set division. You have two relations A and B. I'm sorry, you have two relations R and S. And S is a subset of the columns in R. And what you want is the result is the remaining columns in R, this columns in R that are not part of S. And in order for a tuple from R to appear in the result, it must match every row in S. So this is stronger than a join. In a join, you can appear in the result if you match exactly one row in S. Set division says, no, 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 no. I'm a much stronger form of a join. You can only appear in the final result if you match every row in S. Okay, think back to my two examples. You will be invited to the ceremony if you have visited every park in Tennessee. You will be given an award if you have visited every hotel in our chain. So what we're saying is you have to match every row in S in order to appear in the result. So here we say that we have V and W. So W is going to be our divisor. It's got parks 1 and 2. So A has visited 1 and A has visited 2. So A shows up in the result. B has visited park 1 and park 2. So B shows up in the result. But C has only visited park 1. So it does not show up in the result. So in some sense, you can think of if it evenly divides W, in essence, the answer is 1, it appears in the result. And if it's a fraction, it doesn't. So if you've only visited a fraction of the parks in Tennessee, you will not be in the result. Okay, so that is the remainder. In this case, C1 is the remainder because it did not match all of the rows in S. So that's set division. Okay, so you just need to get a bit familiar with the syntax, the mathematical syntax used for relational operators. So this lowercase, I believe it's sigma, is used to indicate selection, and then you have a predicate. And here's an example, salary greater than 10,000. So it's written as a subscript of this. So if you're doing this on a word processor, you need to make the predicate be a subscript. Let's see if I can find a... you're supposed to use the mathematical operations for and or. So technically, when you write a relational algebra query, you use the so-called relational operators for and or, which are, for and, you say looks like that, and for or, it looks like that. If you are working with Word, I can't create it. Okay, just a sec. You're working with Word. You can certainly do it in LaTeX too. You can do it in HTML. It turns out that there's entity codes. I'm trying to find Word. Thinking about bringing up Word. Oh, this is frustrating. I have two versions of Word right now on this computer, and it appears that the two of them are interfering with each other. Okay, let's do PowerPoint. And so in PowerPoint, if you say insert, you should get an equation mode. You push on equation, you can type an equation, and notice how you get these symbols here. And if you click on the little down arrow, it gives you all possible symbols. If you go down to, I think it's advanced binary. There we go. Advanced binary operations, you will find and or down here. Okay, so when you're doing the homework assignments, one option is to do it on a word processor, and you can find those symbols down there. You can do it by hand and scan it in. That's fine too. Might be easier, but just telling you how I managed to get these symbols. Okay. So projection is this upper capital pi, and then a comma separated list of column names, and they are again subscripted. And order matters. So if you had a select operation, if you put the select operation inside the parentheses, then it would be performed first. Anything in parentheses is performed before anything outside the parentheses. So order matters. So here's an example where I'm projecting several names from the staff relation. Okay, union is just indicated as R union S. Duplicated tuples are eliminated and they must be union compatible. We've already talked. What that means is same number of columns, for each column the same domain. The column names, however, do not have to match. Just the column domains have to match. Okay, so here's an example where we are taking the branch and property for rent. We make them union compatible by projecting out the city, because before they are union, you see that city and address. Actually, these are union compatible without even projecting out city. Because even though the names of the columns are different, the both columns have an integer domain. So this is an example where they're still union compatible. In this case, all we care about is listing the cities, not their addresses. So we project out the city. Sometimes in order to make them union compatible, you have to first project out common columns. Okay, set difference. Anything that's in R but not in S. So our example before with the university, where we had administrators and professors, and we wanted to find all administrators who were not professors, we'd say administrators minus professors. Okay, here we're finding all cities where there's a branch office but no properties for rent. Probably good for closing, because that branch isn't doing anything for us. Okay, intersection. So we've gone through the 5 basic operations pretty quickly because I think they're pretty intuitive. Actually, we haven't gone through Cartesian product. Here's intersection. And it turns out that we can do intersection using set difference. So it's this expression right here. So you first find the set difference. You first obtain everything that's in R and not in S. Okay, and then you take that away from R. So this gives you everything that is R but not in S. Therefore, when you subtract it from R, you're left with everything that is in both R and S. Here's the way of viewing it. Here is R stretching all the way down here. Here is S stretching from here down to here. So this blue portion is the part of R that is not in S. And then when we subtract this part from R, we're left with the white portion. Okay, so that's how we get set intersection using the differences. But we treat intersection as though it were one of the basic operations, but it's not. In the quiz, I ask you what are the basic operations. Intersection is not one of them. Okay, Cartesian product is one of the basic operations. So it's a concatenation of every tuple of relation R with every tuple of relation S. You get that in SQL. If you say select in SQL, you say in SQL select star from R comma S, and you don't provide any where clause, that's Cartesian product. It returns R, the Cartesian product of R and S. Okay, then you can create a join by doing a Cartesian product with selection. So here, what we want is all tuples where we want to select the students that are and what courses they're taking. So we want a list of all students and the courses that they're taking. That's a join of the student and courses relation. The way that's expressed is we first take the Cartesian product of the two courses. Then we filter out only those tuples where the student ID equals the course ID. And then finally, we print the student ID and course ID. So we can see that student 1 is taking CS140 and EC255. Student 2 is taking CS302. So Cartesian product combined with a selection, an equality selection on common attributes is a join. Okay, and we express a join using a bow tie. So we would actually express a join that you would say R S, and then we give the, as a subscript, we would say what is the condition. So we might say R dot ID equals S dot ID. Okay, but that is the bow tie is the join operator. So rather than writing everything out like this, we just use that bow tie operator. Okay, and there's actually, we've already talked about most of these joins. We haven't talked about a theta join or a semi-join yet. You'll pretty much never use a theta join because a theta join is one that can use any of the relational operators. The only one we normally care about is equal, but theoretically, you can do a join of, say, R and S, where A is less than B. But it just, I actually, I've never thought about what kind of operation that would be. I've never run across it, okay? So it's mostly a theoretical notion, but you're allowed to use any of the relational operators. In practice, the only, so you can rewrite that this way, but even though you can write it this way, you would always write it that way. Okay, in practice, the only one we care about is where it is using an equal sign, so that is called an equijoin. So notice you put the joining condition to the right of the bow tie. So the way this is being done is the projection is done here first, projection is done here first, and then they are combined together. That's the order of operations. And in the join, the duplicate column should be removed. So I actually should have removed one of the two IDs here because equijoin is not supposed to duplicate the join column. Okay, with a natural join, you remove the equality condition because you're now saying we're joining, doing an equijoin on all columns with the same name. So sometimes you have to list it out explicitly, but if you do not explicitly list the join condition, it's assumed to be a natural join. Okay. Then the outer join, remember the outer join is where we display all rows in the result, even if they don't have a matching value in the join column. And the way that's shown is with an open thing. So in this case, we're doing a left outer join. If I instead had the bar removed from S, it would be a right outer join. And if I remove both bars, even though it looks like a Cartesian product, it's not supposed to be, it's a full outer join. Okay. And then the semi-join is where we join the two columns, but the result is exclusively taken from the leftmost relation. So in this case, we do a semi-join of R with S, but all we want is the columns from R. So it's as though we do a join of R and S, but then just project out the columns in R. That's called a semi-join. Since we haven't seen that before, I will give you an example. So let's say I want to list the complete details of all students who are taking CS140. So we have to do a join with courses to find which students are taking CS140. But once we have those students, we only want to list the student details, not the course details. And so we do a semi-join of student with courses. Notice that it makes a big difference if we do the selection first. So this is where order is important. If we have first narrowed down the tuples and courses to just one, that's going to be a lot smaller in the Cartesian product than if we first take the Cartesian product of student and courses and then select out course ID equals CS140. So that's why we say order is important in the relational algebra, because it can affect how efficiently the operation is performed. Okay, set division. So I know it's hard to get, so that's why it took me several years to get my head around set division, so that's why I give you a lot of examples. So here we want all the guests who have visited or stayed in every room at the Grosvenor Hotel. So what I've done is come up with a view where all I have is the guest number and the room that they stayed at the Grosvenor Hotel. Okay, and I'm assuming that 100, 200, and 300 are the only rooms. So you can see that 30 has stayed at 100, 200, and 300, so they are included in the result. 20 has stayed at 100 and 300, but not 200, so that would be in the remainder. And 10 has stayed at only 100, so would also be in the remainder. So here we're doing, this is the divisor, this is the dividend. Notice it's a subset, and what's the columns here are the ones that get displayed. And of course, you can project out any unwanted columns. Okay, so here's the preconditions. S, the divisor, has to be defined over an attribute set that is a proper subset of the attributes in R. And then C is the difference, the set of attributes that are in R, but not in S. I know it's not R minus S, it's A minus B, because these are the attributes in R, these are the attributes in S. So these are the attributes that are the result of set division. And again, if you don't want all the attributes in C, you can reject out the ones you don't want. Okay, and it matches every tuple in S. So that's why I say it's a more severe form of a semi-join, because we only care about in the result, we only are printing out attributes from R, so it's like a semi-join, except that instead of matching only a single row in S, you now have to match every row in S in order to survive. Okay, so here's the formal derivation. It's the hardest one. So we first form a set T1 by selecting out the rows in R and projecting them on the C column. So this gives us all possible results. So for example, this might give us all tourists that have visited a park in Tennessee. Now, what we want to do is remove from this list any visitor that has not visited all the parks in Tennessee. So the next thing we're going to do is we are going to find this complicated operation here is the tourists who have not visited every park in Tennessee. So basically, what we're going to do, we take the cross product of T1. So if every tourist had visited every park in Tennessee, this is what the cross product would give us. Then we subtract out from that the actual visitation record. R is the actual visitation record. So if a tourist has visited all the parks in Tennessee, they will be completely eliminated from this result. But if a tourist has not visited all the parks in Tennessee, then the tourist will be left in this result. Okay, so here's an example down here. We'll assume again parks are numbered 1, 2. So this is if every visitor had visited every park, this is what the relation would look like. Okay, but this is the actual relation. This is the actual set of visits. So when we subtract R from this relation, you see that C is going to be left because C has not visited 2. So what's left when we do, when we do this set difference, we're left with C2. And when we project out down to the only the columns we care about, which is the visitor, we end up with C. So now T2, again, is giving us the list of all tourists who have not visited all the parks in Tennessee. So now we can do the set difference. This is T1 is the set of all tourists that have visited a park in Tennessee. T2 is the set of all tourists who have not visited every park. So what we're left with then is the tourists that have visited every park. I know it's convoluted. You may have to take a look at this to really understand it. But that's what set division is. Okay. Okay, so that was the hard part. We're over the hump. Okay. So the relational algebra operations for aggregate operations, instead of using the big pi operation, this looks like a P. I'm happy if you use a P in your write-up. So it is saying that this is the set of column names that I want to see in the result. This is a tau, looks like a T, Greek letter tau. AL is the function list, and it's being applied to R. And the function list is a comma-separated list of aggregate function, comma, attribute pairs. So the aggregate function attribute is being applied to. So for example, how many properties cost more than $350 per month to rent? So we first filter out all rows that are less than 350. Then we apply count property number, and this is the name of the row. I'm sorry, the column will be my count. Now, let's add grouping to it. So the grouping goes on the left side of tau, and it's one or more comma-separated attributes that we're grouping on. So for example, find the number of staff working in each branch and the sum of their salaries. So now we want to count the number of staff and sum their salaries. We're grouping on branch number. And in the result, we want branch number. And then, so what comes first is any grouping attributes you want. And then in order, the names to associate with each of the aggregate columns. So order is important here, because if you put my count first and then branch number second, it's a little bit confusing. So generally you put all the group by attributes that you want first, then a name for each of the columns. So questions about that? Okay, so that's the relational algebra. We're going to move on to the relational calculus. We're just going to get started. The first thing I want to tell you is don't be intimidated. First of all, this isn't calculus. Okay, this is a lot easier than calculus. Okay, it's a logic system, and we're going to just kind of walk through it. It's not super difficult. In fact, on exams and on homework assignments, it seems like students do better with the relational calculus than they do with the relational algebra. Okay, and it's in part because, as I'll show you, you can pretty much, if I ask you to do a question in the relational calculus, you can pretty much first write it out in SQL and then translate it into the relational calculus. Okay, so the relational algebra specified how to retrieve things. It gives an order. The relational calculus just says what we want, but not how to retrieve it. Okay, so it's considered a declarative language, whereas the relational algebra is considered a procedural language. A declarative language only specifies what you want done. A procedural language specifies how you want it done. Okay. So the relational calculus is actually a language based on logic where you're giving a predicate. Okay, that's the where clause or the having clause. And you fill the predicate with values, and that predicate then will evaluate to true or false. You want all tuples that make the predicate true. So a predicate will contain typically variables, and in R, what we care about is what's called the tuple relational calculus. So the variables will range over the rows of a relation, or range over the tuples of a relation. Okay, so what we're going to do is generally have the predicate for each tuple in the relation. We'll substitute values from that tuple into the predicate, And those tuples that make the predicate be true, we will put that in the result set. And if they make it false, they do not make it into the result set. Okay, so the way we specify a tuple variable is by giving the name of the relation, and then the tuple variable appears in parentheses. So this is saying that S is a tuple variable that ranges over the tuples of staff. And then here's your first kind of relational calculus. So it is the set S such that the predicate applied to S is true. So we want all tuples from S such that they satisfy this predicate P. Okay, so here's an example. We want to find all details of staff earning more than $10,000. So we say that staff is S and S dot salary is greater than 10,000. Again, and or, same carrot sticks up and down that you have for the relational algebra. If we want to restrict the result to certain attributes, then we give a comma-separated list of attributes on the left-hand side. Very quickly, you should be seeing similarities between this and SQL. So this is the select statement. Select some set of attributes from, and your from is a list of relations. So those are your tuple variables. Where, and some predicate. So it's from and then and with the where clause. Okay, so again, I often say if you have trouble writing a relational calculus query, write an SQL query and translate it. So here I want to find the salary details of all staff earning more than $10,000. So in SQL, I write it this way. Staff number, select staff number and salary from staff where salary is greater than 10,000. So the select attributes go on the left-hand side. The from things become tuple variables. Then that's and it with the where clause. So now I'm going to quickly go through some of the operations from the relational algebra, show you how you get them in relational calculus. So here we want all tuples from R and S such that, that's a mistake. This should be or, RT1 or, sorry about that. So it should be RT1 or S of T2. So T1 is the tuple. I really messed this one up. Okay. So this should be T1. It's tuple variables that appear over here, and this should be an or, which of course, I don't think I have an equation operator here. Okay, so I will get this fixed, but this is the way it should have been written. So T1 comma T2, where you take it from, you or them together. Okay, here's a join. Again, it should be T1 comma T2. So we are taking R1 and, I didn't get it wrong. Okay, I'm struggling today. This really should have been an and back here. Okay, well, this should have been an and. Basically, you always put the froms wherever you have a from statement, everything is anded together. So it would be T1 comma T2. T1 is ranging over R, and T2 is ranging over S, and T1 dot B equals T2 dot B. So that would be a join. And at this point, I am going to stop, and we're going to finish this up on Thursday. You have already one quiz due on Thursday that deals with the data definition language and views. I am going to push the relational algebra and relational calculus quiz, make it due next Tuesday, and I will probably put, what I'll do is push the homework due date back until Saturday morning. So we'll finish this up on Thursday, and that'll still give you the rest of Thursday and Friday to work on the relational calculus part of the homework. So I'll push the homework assignment due date back to Saturday morning at 6 a.m. I'll push the quiz for the relational algebra and calculus back to next Tuesday. What you do need to do for Thursday is complete the quiz for the data definition language and views. Okay. So with that, I will let you all go. If anyone has questions, feel free to ask them. They have to be fairly quick because I'm going to be headed off to another class. But I also have office hours today starting at 4:15. If I'm a few minutes late, don't worry. Remember, I'm getting lunch. So stick around if I don't show up right at 4:15. Okay, and I will see you all on